Hello and welcome to our second session today on the data science track at PyData Global. Thank you for being here. I'm going to hand over now to our speaker, Eyal Kazin, who's going to be talking about causality, mental hygiene for data science.
Hi, everyone. Eyal speaking from London. Let me just see if I got my slides right. Okay, sorry for the mix-up. I'm setting up. Hi, I'm Eyal Kazin. I'm speaking from London. The slides are available, as well as an article that goes further in detail. You can see it on the side notes, and as well as in the resources tab. And apologies in advance. I have scaffolding going outside my house, so if you hear any noise. So sorry. With that, I believe I can start. Causality is beginning to gain momentum in data science and machine learning circles. Yet while deep learning has experienced a decade-long boom of transformative applications, causality has yet to have its spark moment, at least not yet. Why? Because causality isn't plug and play. Its algorithms demand a shift in mindset, a deeper level of engagement. It isn't just about optimizing metrics, but rather rethinking how we frame problems altogether. Even seasoned practitioners may find causality a bit challenging to apply in real-world settings due to overhead required. As for beginners or aspiring data scientists, it would be reasonable for them to question if they need to invest time in climbing the so-called causal ladder. Over the next 30 minutes, I'll argue that whether or not causality feels immediately applicable in your projects, just engaging with it is valuable in its own right. Why? Because you'll come out with a deeper understanding of what you're trying to solve. In this talk, I'll offer tools for causal reasoning. With them, you'll be better equipped to answer a simple yet profoundly impactful question. Why? Let's explore by embracing causality, how causality can bring clarity, rigor, and insight to our projects, not just as a skill, but as a mindset. So there's no knowledge required, just that you make data-driven decisions, are interested in going beyond correlations. I myself have been doing predictive modeling and analysis for just about 20 years now, and I came across causality actually here in PyData Global in 2020. And this talk is a summary of me playing around with it in various environments. I'll start from the end. These are the messages that I hope that you'll take away with you. First, that applicable or not, causality is good for mental hygiene. I'll introduce two powerful tools to examine applicability of causality. The first is causal graphs. It's a way for us to visualize our understanding of what we're trying to solve for. And identifiability is a framework in order to assess applicability to answer for specific causal questions. So the main takeaway is that causal reasoning can enhance the scientific rigor of what you're trying to solve. I'll start with an introduction about what's the promise and the reality of causality. Then I'll present a case study, and then I'll talk about the said tools. I'll summarize and provide resources that I find useful. So why do we need causality? What's its promise? What's the reality? Let's start with an example of, let's say that you requested from a bank a loan and you've been rejected. Well, the first thing that you want is accountability. And we expect this from highly regulated industry or any industry in general. Just think of your own. So we want accountability on the one hand. Another thing that we want to know is we want an understanding. We'll ask a question like, okay, what do I have to change in order for the bank loan to be approved? For example, my credit score. Standard machine learning and deep learning models do amazing things, but they don't truly understand anything. What they're doing is they're picking up on patterns, but not the actual underlying mechanisms. Sometimes we'll talk about interpretable ML. In my opinion, that's a misnomer. The reason being is that algorithms provide the patterns, and then the practitioner provides the interpretation. And making decisions, either humans or algorithms, or humans based on algorithms, using just correlations can backfire. If you pick up the wrong pattern by slicing or dicing the data in the wrong way, then that could have negative consequences. Here I'm just highlighting one so-called paradox, Simpson's paradox, and basically what it is, it's a misinterpretation of data, depending how you slice and dice it. And for that reason, you want an understanding. And so in causality, what we're doing is, what you do is you shift your mindset from being passive observers of the data, answering questions like what happened, to taking an active role. What would happen if we take a certain action? So questions in causality are framed in the following form. What is the effect of a decision on an outcome? I talked about your credit score on approval of a bank loan, or therapeutic on a recovery, or you can imagine in any industry that you're working on or interested in. So randomized controlled trials come to mind because they're considered the golden standard in many scientific circles for the plain reason that they eliminate many confounding factors. Where that's highly beneficial, there are many disadvantages to this. I'll just highlight the first two. It can be expensive. You can just imagine the logistics behind it. And in terms of feasibility, it might not be physical or ethical. And so what's the alternative? Well, all industries are collecting massive amount of data in a more passive way, and it's much more accessible. And this is not something that's called observational data. And I'm just wondering, can you see my full screen? When I'm looking at it, I don't see it. Okay, I see it now. That's fine. So sorry. So observation. So a lot of work in causality goes into coming up with ingenious ways of extracting cause and effect from observational data. So I'll briefly talk. Our understanding of why smoking impacts lung cancer is perhaps a poster child of causality. How we actually had an understanding, took action, and tested for the impact. And so I'm going to take a lot of artistic liberty in telling this story, but very briefly, we have an understanding of the mechanism between smoking and lung cancer. You don't have to understand the full details, but I will mention, because it is actually quite interesting to learn that where the tobacco industry, they came up with a convenient hypothesis that maybe it's due to genetics, and that's what these two arrows are over here. It turns out that when you smoke, you're depositing some tar in your lung, and we can use that, and that does not depend on genetics, and we can bypass this path of information by using this as a mediator variable. If you don't understand, that doesn't matter. What's important is in scientific realms, there is an understanding of the mechanism between smoking and lung cancer, and we can take action on that either by advertising on cigarette packets or taking off commercials from the media. And then you can track, for example, metrics of interest, like number of cigarettes sold versus the rate of cancer deaths. And you can see that one drops after another due to certain points of action. So what's my point? My point is that I draw a very rosy picture of the promise of causality, going beyond correlations, making perfect decision-making, and shifting from being passive actors of answering what happened to what would happen if. So why don't we see causality as abundant as deep learning? Well, the main reason is because it's hard. There are many reasons that it's hard. For example, there are a lot of assumptions involved, some questions you can't answer. And I'll focus here on the cognitive effort that it requires a lot from both technical staff and stakeholders, and hence it's also more time consuming. Also, the interesting thing is that when you learn about a tool, you have to beware of treating it as a hammer and chasing for nails. And that has been my mind thought for the past few years, but I feel it has evolved. And it evolved to my understanding that causal inference isn't your standard tool. It's a frame of mind. It may be, and the reason for that is that it can be useful to enhance interpretation. And by that, I mean, by assessing its applicability is valuable in its own right, even if you can't apply causality at the end of the line. Just using the tools can help you understand what you're trying to solve for. And now I'll demonstrate on a case study, and this is something that I experienced in my work. So what I was doing, I was creating a standard supervised machine learning model, which was trying to predict for a target variable y, which depended on many features. Here I'm just highlighting the first two, in which all of them are correlated. And so I get a score, 0.8. And then it becomes more interesting when I want to compare this versus a benchmark model. X1 correlates the most strongly with Y, and we understand why it correlates with Y. And so that's our benchmark model. And interesting, and the benchmark model only results in the same predictive score. So adding all these features that are correlated with Y did not improve the outcome. And so that seems like a paradox. I also asked the model, well, what are the most important features according to the setup? To add insult and injury, it said that yes, X1 is the most dominant one, but the other features, X2 here represents the other features, actually had a non-negligible contribution. And so then I realized one of the main learnings of causality is that the vocabulary of statistics is quite limited, and I need causality in order to understand what's actually going on here. And so long story short, what I realized is that X2 had a direct effect on Y, but it's overshadowed by the common cause X1. Now, that sounds complicated, and it is, but the beauty about causality is that you can actually draw this out, and it's much more simple once you do so. And now I'll say the same exact thing, but on a graph. So here you can see Y, and it depends on two parameters, X2 and X1, but the causal effect of X2 is much weaker. X1 actually impacts both. And so the strong correlation that I saw between X2 and X1 was actually flow of information, and this is called a backdoor path. Yeah, and so what was the takeaway from this? The takeaway from this is that on the one hand, this was a great insight. It did improve the predictive power, but it did lend a lot of other things. For me, the most important thing was I had better interpretation of what I was dealing with. I could I had confidence in the report that I was making, and there was that insight. And something I couldn't do with statistics and machine learning heuristics, for example, so-called feature importances, and it's something that I need to put a causal hat on. And that actually sparked a conversation within our team about us wanting to provide more resources to use this. For the rest of the talk, I'll focus on this enhanced interpretation. And I like this quote by Judah Pearls, who's considered the godfather of causality, who says that causation is not merely an aspect of statistics, but it's an addition. And from here, I say causality reasoning enhances the scientific rigor of problem solving. If you don't like the term scientific rigor, then you can say enhanced interpretation. In causality, we say that the story behind the data is as important as the data itself. For this purpose, causal graphs actually help us visualize that story behind the data. So we'll talk about this. This is the first of two tools, and we'll also talk about its utility. So this is what a causal graph may look like, and which what it does is describe the qualitative relationships between the parameters. So you can think of it describing each node here is a parameter, and it describes who's listening to whom. And what we're doing here is we're articulating what the data generation process actually looks like. And what do I mean by that? What I mean is that we're articulating what we think the underlying mechanism is. And this is something that we can test for. Specifically, DAGs are a subset of causal models, the direct acyclic graph. And the acyclic part means that there are no cycles in it. For example, if you start with A, there's no path that leads back to A. The reason that's powerful is that simplifies the maths, and you can and encodes conditional dependencies between the parameters. And this is something that, this is my understanding of the world. All models are wrong. Some are useful. And that means I can actually test for this. And for example, A and B are independent. A and C actually have a correlation. If you look at data, there will be a correlation, but they will be independent if you control for both for D and B. That's what's written over here. So that's very powerful. And this gives us a mean to better interpret our data, just like I did with the machine learning paradox. If you can better interpret your data, you'll be able to create better experiments. Another very powerful aspect of this is that if you trust this drag and you have another project that overlies in its domain, then you can transfer this knowledge. And notice that all this I've done qualitatively, and then when I want to test it empirically with conditional probabilities, then I use data. The key takeaway from this section is that the reliability of a DAG is a key assumption in causality. In textbooks, you're provided with DAGs, but in the real world, you have to actually build it. You have to construct it on your own, and that's called causal discovery. So I'll describe this from a qualitative aspect and talk about complexities of it. So what you need in order to create a DAG is you need a domain expertise, someone who has lived and breathed these parameters to a certain degree, and also you can consult with the literature. This is done, again, qualitatively. And then you can test your assumptions using data. So there are automated processes in which you can do this, especially if the DAGs if there are a lot of parameters involved. But for one's own mental hygiene, I suggest doing this manually. So start small, no matter how big the system is, and play around with what you think is going on at the core of the area of the question you want to ask. And now we'll spend some time actually doing this manual causal discovery. What I'll use is the classical case of correlation is not causation between ice cream sales and drownings. What I like to do is I like to write clear statements about my understanding of the system, and each time another parameter arises, I like to add that to my list. For example, drownings have a spurious correlation with ice cream sales, but drownings are not caused by ice cream sales. Ice cream sales are driven by it being sunny, etc. So once I have all this laid down in front of me, then I like to draw the graph, the arrows between them, and this is something that we can test once we have data. Of course, I described here a toy model. In real life, this can be much more complex, and there are two main aspects that depend how complex the system is how much you can rely on the domain expertise, and also how much control you have over the data generation process. What do I mean by that? Well, it's easiest to understand this by looking at the least complex situation. That's when you have full control over your data. It's either synthetic or simulated, and so something that you can turn the knobs with. That means you understand more in detail, like where the arrows are pointing. The other side of the extreme is when you have no control, fully observational. Sometimes you might not even know the direction of the arrows. In between is RCTs and A/B tests, in which you can control for one or more parameter. So what the takeaway from this slide is that if you have full control, like synthetic or simulated data, then you're highly likely to benefit from causality, and you should definitely look into that. If you don't have, not to be discouraged, the whole point of this talk is the fact that just by assessing causality is valuable in its own right. So just playing around with, just trying, you learn a lot, even if at the end of the day, you're doing a standard machine learning model. So just to summarize this section, causality, DAGs are useful for causal interpretation. By improving that, you can improve how you do experimentation, and it can transfer also knowledge of that DAG. One more point I'd like to spend some time on is importance the utility of DAGs to justify parameter control. Why is this important? Many scientific studies boast about how many parameters they control for to get to the conclusion, but it's rare that they actually justify it. Why is it important to justify? Well, just imagine, for example, these two simple DAGs. You want the relationship between X and Y, and you want to know, should I control for A or not? Well, in this case, on the left, you want to resolve for it, because that will control for any spurious correlations between X and Y. And this is a mathematical way to say it. X is independent from Y, conditioned on A. On the other hand, if you have and on the other hand, in this case, you do not want to control for A, because that will generate a spurious correlation. And so this is something that's well known for students of causality, for example, economists. But many scientists, including myself, I did astronomy for 12 years, and I was quite embarrassed that only 4 years ago I realized that this was a thing I should have been aware of. Just to summarize this section, we talked about the fact that causal discovery is used to build for DAGs and test for reliability, and we talked about the complexity spectrum. So you have a DAG, and now you want to ask causal questions from it. And for this, we have a framework called identifiability, which we'll talk about now. What it is, it's a framework to assess minimal sets of parameters required to quantify a specific causal effect. If that doesn't mean anything to you, that's fine. I have a few slides in which we'll learn by example, in which it will be clear what that means. For now, I'll just mention that it helps assess which parameters are sufficient or necessary or as important unnecessary in order to answer for specific causal questions. A benefit of knowing what's unnecessary is potentially you can lower the budget of your project. First, this is the first of a few examples. Let's assess the impact of smoking on cancer. Okay, so what are minimal sets of parameters? Well, we can either solve it by having, we don't need all four. We can solve this by either having smoking, DNA, and lung cancer. That's a minimal set of parameters required. Or you can have smoker, tar, and lung without DNA. So how will we parameter our labels? Well, DNA and tar, assuming both of them are there, we have access to both of them, are both sufficient but not necessary. But if we don't have DNA, for example, imagine scientists in the 1950s before the Human Genome Project in the year 2000, well, they didn't have access to DNA, so that means tar for them would have been necessary. The second example is here we're extending the ice cream sales and drownings. And now we're interested in the impact of lifeguards on drownings. So the question is, what are minimal sets of parameters in order to get this causal effect? Well, it turns out there's only one. Lifeguards, swimmers, and drownings, that's all you need. Here you have, again, this backdoor path that we want to control for. You don't need this whole branch over here. You don't even need beachgoers or knowing the weather. In the next example is actually a question for the audience. Feel free to reply in the conversation section. So let's say what's the minimal set of parameters to assess the impact of ice cream demand on sales? So I'll leave that as an open question. I'll be here later if someone wants to discuss, and I actually have the answer in the article. So far, so like quite simple to understand. Models quite small, but you can imagine much larger DAGs. And the really cool aspect of this is that solving for this, once you're trained, is easier than you might think. For example, I know nothing about genetic dissection, but yet with training, I know you can solve for this. For example, we want to solve, we want the causal impact between the green and the blue. And so here's the causal path, but there are many biasing paths, and computer says, well, we have to control for one of these three sets. So these are, again, the minimal sets, and I'm going to choose the middle one. So I'm controlling for this and this, and now it says it's fine, we can assess causality. So the takeaway from here is that identifiability is useful to assess if we can answer for specific causal questions from a DAG. And by so, you're labeling your parameters as sufficient, necessary, and unnecessary. And by identifying that, you'll be able to reduce the budget of your experiment. That, of course, depends on what parameters you actually have already measured. Those you can label as observed or unobserved. And if it's unobserved, then could you potentially observe them? Should you set a budget for that? Or are they unobservable? And in that case, you'll have to redefine your question. So last few slides, and then I'll provide resources that I find useful. I like this quote that was popularized by Michael Bloomberg, in which he talks about the fact that in order to fix something, you have to measure it. Hopefully by this stage of this talk, you'll appreciate my paraphrasing of this. It's not enough just to measure it. You have to be able to articulate what you have measured. And this is related to another quote by Judah Perel, which is that the fact that data does not compensate for your assumptions about it. A few more takeaway points, just reiterating, assessing applicability is valuable in its own right, regardless of the fact if you're going to apply causality at the end. For example, the machine learning paradox that I talked about earlier. And this will bring scientific rigor to your project because you're in a better position to articulate how the data was generated. You can document this for future projects. You'll improve the way you interpret existing data, and you'll be able to design for future experiments. Of course, there's no free lunch. This requires a lot of cognitive effort and can be more time-consuming. The main messages to take home, first of all, that applicability, that if causality is applicable or not, it's good for mental hygiene. DAGs are a means to visualize that story behind the data. The reliability of them is key for causality, and we talked about how we build it with causal discovery. And then we talked about identifiability as a framework to assess which questions we can and cannot ask from our data and which data is required. I put all these opinions in more details into this article, so feel free to look it up. Those who are starting their journey in causality, I gave a talk a few years ago in PyData Global, in which I actually I explain actually what that means. The story behind the data is as important as the data itself, and I provide resources and visuals that I found very useful to in order to convince myself that yes, I want to start to learn causality. Once you're ready, once you feel that you're ready, for me, I felt that mastering Simpson's paradox was my gateway drug in order to understand causality, and so I wrote a piece about that. And it comes with caution. Once you understand Simpson's paradox, you'll never look at data the same way. So you have been warned. And this last piece, I wrote about a fun brain twister called Monty Hall, in which I look at it at different angles. And one of the questions I had from it is it can we use it as an analogy in real world settings? And I actually use a DAG in order to answer for that. And you can read here my conclusion. So a few resources that I found useful to begin my journey. These first two by Judo Pearl, Popular Reading, and a textbook. And if you want to apply with causality, I highly recommend this by Alexander Molak. Then here's a course by Neil Brady, which is everything that you want from a course. It's clearly explained, it's thorough, and it's free. If you're ready to apply in real world settings, I highly recommend these talks by Dimitra. Specifically, I love this slide in which she compares traditional versus causal data science pipelines. So a very useful resource. And I do want to send a massive thank you to James Barker, the doodle master who created all these lovely visuals. And with that, thank you. I'll be here for the rest of the conference, and I'll be glad to take questions if there's any time. By the way, I can't hear, I couldn't hear the speaker before, so if you can chat, that might be best. I've been pretty bad at looking at questions. I haven't looked at questions. So I'll actually look at the questions for someone very interested. Okay, so I provided the studying materials. Thank you for that question, Miguel. Oh, software. Yeah, so software, I think I have, I recommend DoI. I think I have a slide for that. Gosh, do I have a slide here? No, I don't have a slide here for that. But yeah, I recommend DoI. I've played around with DoI. Yeah, so it's a framework in which, it's a shame I don't have a slide here. Let me pull it up, just one second. Yeah, so I don't have DoI. I don't have my slide here. It's in the, but yeah, look it up. It gives you a framework for both exploring your. It gives you a framework for exploring your DAG, testing for reliability, doing that identifiability, and then also quantifying the causal effects as well as trying to refute it. So, for example, if you forgot like a common cause or something like that, it will create common causes in terms of knobs and switches just to see how reliable that is. So 4 stages, and it's a great framework. Are there any further questions? Sorry, this is a bit embarrassing that I can't hear anything, so I don't know what's going on.
No worries. Sorry about that. I think that's all the time we have. Thank you for that awesome presentation. I really enjoyed that, and the illustrations are super fun. So thank you again, Eyal. The next session on the data science track today is the art of wrangling your GPU Python environments. I hope to see you all there. Thank you again, Eyal.
Thanks. Thank you.